Dr. Zacher presents.
Blue over red. Stability criterion of Leonhard-Zacher for closed-loop control. Hello, here is Dr. Zacher. This video is about stability criterion, which was proposed in my automation letters and was registered in the German National Library. The fully description of this criterion, which I called 3 Bode plots method, you can find in 3 books shown below. Overview of known stability criterions in frequency domain.
Nyquist stability criterion, proposed 1932 and commonly used till now. Mikhailov stability criterion suggested 1936. It is rarely used because it is needed to calculate the transfer function of the closed control loop. Leonhard stability criterion, which was proposed 1940. It has many advantages against Nyquist and Mikhailov criterions, but the adjustment of controllers is so complicated that today this criterion is not described in books for linear control systems and not used for linear systems.
Now let me present my own stability criterion, which has inherited the advantages of the Leonhard stability criterion, but improved it as far that the practical use becomes easy and effective.
The Bode plot of the plant should be given. It is shown with the blue curves. Besides of this, the magnitude of a symmetrical controller as the red curve should be dropped in the diagram. The intersection of both curves is the point D. After that, the phase of a phase symmetrical controller, also as the red curve, will be dropped in the diagram. That's all. Now let us check the stability. Another example.
As you have seen, there are 3 Bode plots in one Bode diagram. Bode diagram of the plant. Magnitude of symmetrical controller. Phase of phase symmetrical controller.
But what means the expression, blue over red?
The definition of the expression, blue over red, is given in my books and shown below.
But 2 questions are left. What is symmetrical controller, and what is phase symmetrical controller?
The detailed explanation is given in my book. In this video it will be answered upon examples. The Bode diagram of API controller is well known. There is no need to explain it. Let us split the Bode diagram of the PI controller into 2 plots, Rotating the magnitude 180 degrees around symmetry axis LG equals 0 decibels, to get the symmetrical controller. To get the phase symmetrical controller, we will do the same, rotating the phase 180 degrees around symmetry axis L phi equals minus 90 degrees.
The Bode-diagram of a PD controller. The symmetry axes are referred to LG equals 0 decibels for symmetrical controller and L phi equals minus 90 degrees for phase symmetrical controller. PID controller. Proportional P controller. Integral I controller.
Example 1. P controller with integral I plant.
Independent of the position of the intersection D, the blue is above red. That means the closed loop is stable by all possible positive values of controller gain.
Example 2. P controller with double I plant.
Independent of the position of the intersection D, the blue is not above red. That means the closed loop is unstable by all possible positive values of controller gain.
Example 3. P controller with PT1 plant.
Independent of the position of the intersection D, the blue is above red. That means the closed loop is stable by all possible positive values of controller gain.
Example 4. P controller with PT2 plant.
By the position of the intersection D, see figure on the right. The blue is not above red. That means the closed loop is critical. By the position of the intersection D1, the blue is above red. That means the closed loop is stable.
Example 5. PI controller with unstable PT2 plant.
Left from the intersection D, the blue is not above red. That means the closed loop is unstable. If the intersection point is D1, then blue is over red, and the closed loop is stable.
Example 6. A plant that is controlled with the PIDT1 controller is given with the Bode plot, blue curve. The desired phase rand is 60 degrees.
As far as the transfer function of the plant is unknown, the parameters of the controller are arbitrarily chosen. The magnitude of symmetrical controller and the phase of phase symmetrical controller with these values are drawn up in the figure on the left. The closed control loop is unstable, because at the intersection point D, the blue is not over red. Both phase responses intersect at the point B critical, and define the area with blue over red stability area. If the intersection point is D critical, instead of D, the control loop becomes critical. On the left side of critical point B critical, there is blue over red, that means the closed loop becomes stable. Selecting the required phase reserve of 60 degrees, by the intersection point D nu, the magnitude response of the symmetrical controller should be shifted to this point. The required change of the controller gain is read from the Bode plot. The new value of the controller gain, needed for the upward shift of the magnitude of the symmetrical controller, is calculated below. The Bode plot with the calculated controller gain is shown below.
By the intersection point D nu, the closed loop is stable with the required phase reserve of 60 degrees. Summary.
Advantages of Leonhard-Zacher stability criterion. No transfer function of the plant is needed. It is needed as only the Bode plot of the plant, which could be defined experimentally. No calculations of transfer functions of open or closed control loop are needed.
The stability analysis of the closed loop and the adjustment of the controller is very simple, as described below. That's all. Thank you for attention. Goodbye.
More about Leonhard-Zacher stability criterion.